The air standard diesel cycle is shown in the picture. This is the ideal cycle for the diesel engine. Which is also called compression ignition engine. Or CI engines. In this cycle, the heat is transferred to the working fluid at constant pressure. The heat transfer at constant pressure, QH, at constant pressure. This process corresponds to the injection and burning of the fuel in the actual engine. Ignition and burning fuel. This part, constant pressure heat addition. This part and this, this point in the TS diagram is here, QH. Since the gas is expanded during the heat addition in the air standard cycle, the heat transfer must be just sufficient to maintain constant pressure. When state 3 is reached, this, and also in here, this part, the heat addition ceases and the gas undergoes an isentropic expansion process to 3 to 4 isentropic expansion process until the piston reaches the bottom dead center. As in the air standard Otto cycle, a constant volume rejection of heat at bottom sector replaces the exhaust and intake pressure of the actual engine. The efficiency of the cycle is given with this relation. Eta on QH. Or we have QL in a constant volume and QH is a constant pressure process. Or we can write equals to 1 minus T1 The isentropic compression ratio is greater than the isentropic expansion ratio in the diesel cycle. isentropic expansion ratio, compression ratio is greater than the isentropic expansion ratio. In the diesel cycle. Consider this picture again for the diesel cycle. In addition, for a given state before compression and a given compression ratio, state 1 and 2, the cycle efficiency decrease as the maximum pressure increase. So the cycle efficiency decrease with the maximum temperature increase. Maximum temperature is T3. This is evident in the TS diagram because the constant pressure and constant volume lines converge and increase the temperature from 3 to 3 prime. Here requires a large addition of heat and result in relatively small increase in work, so decrease the efficiency. A number of comparisons may be made between the Otto cycle and diesel cycle, but here we will note only two. Consider Otto cycle. The difference between Otto cycle and diesel cycle. The Otto cycle has higher efficiency in practice. However, the diesel engine can operate on a higher combustion ratio than the spark engine. The diesel engine can operate at higher compression ratio CR than the spark ignition engine. The reason is that in the spark ignition engine an air-fuel mixture is compressed and detonation because a serious problem if too high a compression ratio is used. This problem does not exist in the diesel engine because only air is compressed during the compression step. Therefore, we may compare on Otto cycle and diesel cycle, and each case select a compression ratio that may be achieved in practice. Such a comparison can be made by considering Otto cycle and diesel. The maximum pressure and temperature are the same for both cycles, which means that Otto cycle has a lower compression ratio than the diesel cycle. This is evident from TS diagram that in this case the diesel engine cycle has the higher efficiency. The conclusion drawn from a comparison of these two cycles must always be related to the basis on which comparison has been made. The actual comparison ignition open cycle differs from the air standard diesel cycle in much the same way that the spark ignition open cycle differs from the air standard cycle Otto cycle. The next section is the Stirling cycle.